In the grandeur of the universe, the tapestry of life may be woven from stranger threads than we ever dared to dream, and spun from materials far different to our own. As we've studied the immensity of the cosmos, we've spent decades searching for life as we know it, clinging to the belief that the universe must be teeming with carbon-based organisms like ourselves. But what if life's building blocks are not limited to the familiar carbon atoms that compose our DNA and proteins? What if, out there among the stars, there exist beings unlike anything we've ever imagined, life forms fashioned from the silicon of alien worlds? Today, we'll embark on a journey of imagination and scientific exploration to ponder the possibilities of silicon-based life forms, creatures that could thrive in environments hostile to our kind and challenge our very understanding of life itself. I am your host, Isaac Arthur, and I hope you'll join me today as we delve into the realms of silicon-based biology, where the chemistry of the cosmos takes on new and exotic forms. This is not our first look at alternative chemistries for life, and when we explored ammonia-based life forms earlier this year, there were many requests that we should look at other chemistries, silicon-based life forms being foremost amongst them. We may cover those others down the road, but silicon turns out to be a big enough topic on its own. So grab a drink and a snack and relax. We'll be here for a bit. And make sure you like and subscribe to the show and hit the notifications bell if you want alerts when new episodes come out. Now, odds are good that you've heard folks mention the possibility of silicon-based life forms before, and for those curious, we are not discussing machine intelligence, AI, and computer brains today, except as a minor tangent. The concept of silicon life predates the discovery of the silicon semiconductor, which is from the mid-1950s, and would not become synonymous with computers or robots for some years. Indeed, sci-fi from that era and earlier focused on calling them iron-based life, or references vacuum tubes, glass and steel constructs, like the skyscrapers that were beginning to dominate skylines of bigger cities. While silicon life forms as a concept was probably popularized by the Horta in Star Trek's 1967 episode, The Devil in the Dark, the idea is much older. Way back 132 years ago, in 1891, German astrophysicist Julius Scheiner suggested that silicon's similarity to carbon might make it an alternative for life out among the stars. And at the time we couldn't distinguish our galaxy from the wider cosmos, and had no idea about the age of the universe, or how elements like carbon or silicon came to be. But if you've seen the periodic table, it's hard to miss silicon there right under carbon and sharing many of its features. Critically, that they are both tetravalent, tetra meaning 4 and referring to the outer layer of electrons of an atom, the valence electron shell, which has 8 openings, so any atom that is tetravalent can have 4 covalent bonds to other atoms. And in the case of carbon, this is how we have methane, composed of 1 carbon atom with 4 hydrogen atoms attached to it. How many covalent bonds an atom can take is important, especially for our big 3 of oxygen, nitrogen, and carbon, which are divalent, trivalent, and tetravalent respectively, or it would have 2, 3, or 4 bonds. Those 3 are also incredibly common, with carbon being a byproduct of helium fusion and a common substance in the universe, while the CNO cycle, or carbon-nitrogen-oxygen cycle, fuses carbon into nitrogen and oxygen, both very common in the universe too, especially oxygen. All 3 have very common partnerships with the most abundant atom, hydrogen, to form oxygen plus 2 hydrogen, water, nitrogen plus 3 hydrogen, ammonia, and carbon plus 4 hydrogen, which again is methane. Those 3 substances are most of what your typical comet is made from, and are what we are usually talking about in space context when we reference volatiles and organic building blocks, and make up a large fraction of the matter in this universe once we remove dark matter and hydrogen and helium. Indeed, it's the largest fraction of atoms made since the Big Bang. Most hydrogen and helium date back to the first couple minutes of the universe. It's no surprise then that something similar to carbon by being tetravalent would interest us as an alternative, and indeed the methane equivalent of silicon exists and is called silane or silicane, and is 1 silicon atom plus 4 hydrogen. There are other tetravalent atoms, germanium for instance, which was our preferred semiconductor material for a time till we switched to silicon, which is better at higher temperatures, And that's where silicon as an alternative to carbon for life starts coming into play, places where carbon chemistry couldn't function for the heat. As we discussed back in our ammonia-based lifeforms episode, what we really mean by carbon-based life and water-based life is chemistry built on carbon but inside water as a solvent. And ammonia is a good solvent too, if not quite the equal of water as a solvent, but freezes at a much lower temperature than water and thus opens the door to life in very cold places. Silicon goes the other way, opening the door to hotter temperatures. And as mentioned, ammonia is an option because nitrogen is quite common in the universe, but there are about a third as many silicon atoms as nitrogen and around a tenth as much as carbon. More importantly, here on Earth, in our crust, silicon is the second most abundant element, right after carbon, and indeed most of our rock and dirt and minerals are made of those two substances. Ironically, silicon's abundance here on Earth, compared to carbon or nitrogen, actually hurts it as a candidate for life, since it is more abundant than both, neither making up even 1% of the matter in our crust, and yet the more abundant silicon is a relative non-factor in the life that did form here. One caveat, it may be that silicon-based life is far more common on planets like Earth, and we just happen to be the freak case where carbon life popped up first, and became dominant and crushed any competitor that formed later. But that seems like a stretch. Still, when you only have one example of something, in this case, life, we should not take for granted that it's the normal situation. Silicon has other things that make it weaker for possible organic or quasi-organic chemistry, and as an example, silicon is much more massive than carbon, more than double, which means it puts a greater strain on molecules it is part of, though it also makes it more temperature resistant since an atom of it jerks around less at the same temperature. Silicon and carbon polymerize differently too. Carbon polymers are frequently long chains of carbon attached to each other, and polyethylene, for instance, is basically a long chain of carbon atoms, where each carbon atom has a bond to one carbon on either side of it, and one hydrogen on either other side of it, much akin to hydrocarbons we use for fuel, while silicones are made of silicon to oxygen, not silicon to silicon linkage. Carbon forms these large scaffolds of atoms on which other atoms can latch on, and thus is the basis for our organic chemistry and life. This is a major reason why we talk about carbon-based life at all, given that it's not even a fifth of your body's mass, which is almost 4 times more weight of oxygen and is heavily outnumbered by hydrogen atoms. It is not the only scaffolding non-metal though, nor is it just silicon. Boron and sulfur are other examples, and they too get suggested as an alternative basis for life. Silicon also readily bonds to oxygen to form simple silicon dioxide, most commonly as quartz, and again silicon and oxygen make up most of the ground you're standing on. Silicon dioxide is highly stable and inert compared to carbon dioxide. Silicon dioxide isn't particularly soluble in water either, which is okay as we're mostly interested in hotter places than liquid water would be at, but helps explain why life on Earth is made of carbon, not silicon. No, what we are really thinking of in regard to silicon-based life isn't it arising on Earth-like planets or cold frigid ones where ammonia might be king, but rather on hellishly hot planets like Venus where carbon is actually very abundant in its atmosphere, but where carbon chemistry isn't viable from the viciously hot temperature. Odds are you have a pair of silicone mitts at home for pulling hot objects out of your oven or some silicone utensils for your non-stick cookware, and if not, I'd strongly recommend them, but it is temperature resistant, also solvent resistant too, again making it tricky to couple with water or ammonia as a basis for life. It does react to hydrofluoric acid, which like ammonia has also been suggested as an alternative to water as the solvent for life-bearing chemistries, but in our context today we are more interested in silicon using molten metals as a solvent. As an example, aluminum melts at 1220 degrees Fahrenheit, or 660 degrees Celsius, and is very common, while tin melts at a mere 449 degrees Fahrenheit, or 232 Celsius, and lead at 621 Fahrenheit, or 328 Celsius, both common components of the solder we use on circuit boards and for that reason, plus being conductive of course. Incidentally, tin, lead, and boron are also tetravalent elements like carbon, silicon, and germanium. They are also decently common, and one reason why we have a lot of silicon in our crust is that it is low density and floats in molten metal. So we figure big rafts of the stuff commonly surface on molten worlds as they cool, leaving a crust heavy with it. And silicon can't handle monstrously high temperatures. Silicone doesn't melt but will catch on fire at 840 Fahrenheit or 250 Celsius. Quartz melts at over 3000 Fahrenheit, for instance. Amusingly, that means there is a non-zero chance that silicon-based life did live here on Earth way back, and was killed off as the planet cooled or when that dwarf planet, Theia, smacked proto-Earth and blew our crust off, from which the moon later formed, and onto which we assume a long rain of comets later fell to give us oceans. But planets start hot, and can stay that way if near their sun, and it isn't too hard to imagine silicon life on a Venus-like planet or living in the lava tubes of some volcanic or Chthonian planet. Chthonian planets are believed to have originally formed as super-Earths, gas giants, or ice giants, similar to Jupiter or Neptune in our own solar system or smaller. However, they have undergone significant atmospheric loss over time from being that close to their sun. Photoevaporation, thermal escape, or interactions with their host star strips off their atmospheres and lighter elements, much as Earth lost most of its hydrogen and basically all of its helium. So you get left with a big hot ball of metal and silicon, and probably a lot of oxygen still too. These sorts of planets are likely to be pretty common in the galaxy, and also likely high on tidal forces, which might be beneficial for life. Could they hold not just life, but complex life? Well, perhaps. We normally talk about habitability in terms of surface oceans and atmosphere. Subsurface oceans are entirely viable too. Indeed, biologists generally favor life originating deep in the oceans. The problem is the power source though, as the sun allows photosynthesis and dense biomass in ecosystems, which we assume seriously helps move evolution along to let intelligence possibly develop. Subsurface oceans on moons like Europa can probably have life, as tidal forces from Jupiter on its moons is big enough to power a modest ecosystem, but while contemplating giant alien kraken on Europa is fun, it's not very likely we'd see big critters there or complex ecologies with such a limited power pump for the ecosystem. Hence the focus on surface oceans and atmosphere in our hunt for life, along with biosignatures being easier to see astronomically if they were on the surface, of course, rather than buried down in caves or lava tubes or magma seas. However, the key is a large energy flux, and a molten planet tightly wrapped by its own sun absolutely fits that bill. The problem isn't if there's energy to run the chemistry of life in these places, but if the temperatures are too hot for any life. And the answer is no. We could absolutely design some sort of artificial life form for this, it just wouldn't be carbon-based, unless we're talking diamond and graphene types of carbon, not the classically squishy bag of water that best describes life forms on Earth. Whether or not a natural life form could develop is harder to say, as evolution has to follow a path of minimum steps that engineered life forms or freak improbabilities like Boltzmann brains do not. Heat is not the only extreme that might permit silicon life. Again, it isn't soluble to the same degree and to the same things carbon-based life is, so some acidic environment might work well for it. Extreme conditions such as high temperatures and radiation might be suitable for these life forms, expanding the possibilities for habitable exoplanets. So we're definitely seeing room for silicon life in places carbon-based creatures should fear to tread, but I think we also need to acknowledge that it has some key problems, all the way down to the basic DNA, or silicon equivalent, which we'll label sDNA. Carbon-based DNA relies on a long chain of nucleotides, with each nucleotide composed of deoxyribose, the D in DNA, and a sugar, a phosphate group, and one of 4 nitrogenous bases, adenine, thymine, cytosine, or guanine. These bases form pairs AT or CG that encode genetic information. Silicon, although again tetravalent like carbon, does not readily form the stable, intricate, and versatile molecular structures that are essential for genetic material. Silicon-silicon bonds are generally weaker than carbon-carbon bonds, and silicon compounds tend to be less stable in water, which is a crucial environment for life as we know it, and why hotter areas without water interest us. However, in speculative discussions about silicon-based life, we do have some ideas that have been proposed for silicon-based genetic-like molecules, or again, sDNA. One such concept is the use of silicones, which are silicon-oxygen compounds, to create a chain or polymer structure that could store information. Silicones are more stable in some conditions than other silicon-based compounds, but they are still quite different from carbon-based nucleotides. This is all very speculative though, and I feel obliged to emphasize that the viability of silicon-based genetic molecules remains highly speculative, and there is currently no empirical evidence to support the existence of such molecules in nature. Now we have the basic building block of life, such as these silicones, and something for them to do chemistry in, a solvent like water, or acid or molten metal. But we need energy, or more accurately, energy flux. Heat offers that, and we might see some interesting silicon life forms, such as those that were basically a big thermocouple running on geothermal energy. Maybe something like a giant silicon tree growing from deep in the molten sea to up into the empty sky above to radiate heat away and run on that flux. Or a mobile version of that might be some huge silicon whale, or kraken, or a very long Dune sandworm that ventured through the lava or the huge lava tubes left inside some slowly cooling but still viciously hot Chthonian planet. They might also run on electromagnetic radiation. Remember, silicon is our ideal semiconductor material and the basis of modern solar panels, and I think it is plausible enough to assume that photosynthesis might be no harder to evolve than some equivalent of a biological thermocouple or photovoltaic cell. This opens the door to some interesting options for life forms, as we might easily have creatures with quartz hides instead of skin, or quartz bark trees with roots that drank in magma, or were long hybrids of wire, root, or hair that were very high in thermal or electrical conductivity. You might have weird options like an organism that was a gas bag made of silicone latched onto a gas vent from a molten interior to a low pressure near vacuum airless surface above, feeding on those mineral-rich gases while soaking up sunlight from its natural photovoltaic cells. Indeed, that's the sort of scenario where life might evolve on a moon like Io, tidally racked and volcanic from Jupiter's gravity, and be able to spread out to other nearby moons or a planetary ring like Saturn. In our Void Ecology and Space Whales episode, we contemplated that scenario more, and options like a natural Kardashev 2 civilization or Dyson swarm of quasi-organic critters who might be no smarter than a whale or a fish or even a coral reef. It is not hard to imagine silicon-based life forms manifesting as something like a coral reef made of quartz instead of calcium carbonate, though we should not assume silicon-based life is all silicon any more than we are all carbon, and they may well swim through oceans of molten lead with skin made of iron or titanium or tungsten. On the flip side, just because silicon can survive high heat doesn't mean it's unable to handle great cold either, and I could imagine worlds where slabs of quartz among the ice ran on low-energy flux but ultra-efficient low-temperature conductors, or a planet whose sky was dark from a thick atmosphere the sun could not penetrate, but which had storms that ravaged that planet and wrecked any carbon life, but the quartz monolith shot through with veins of metal soaked up the lightning and ran some mind upon it that danced on the hazy edge between a brain and a computer. And while it's not our topic for today, another type of silicon-based life would be robots and computer minds, and if it is the habit of alien civilizations to send out von Neumann probes to explore for them, and to conclude that colonization is harder than they wish to pursue, we might see the mutant remnants of those self-replicating probes slowly shift from being a machine with some lifelike characteristics to a life form that is based on silicon and has some machine characteristics. The possibilities seem vast, but that said, we now have plausible chemistry and various ecological niches available from various power supplies, allowing large and diverse ecosystems, and we can move to the SETI aspect of silicon life. In other words, we know where it might live, so how can we spot it and recognize it? What are some possible silicon biosignatures? These are hard to say for biosignatures, as without knowing the chemistry they use in any detail, things like waste products are hard to guess at. If it were silicon dioxide, the way carbon dioxide is a waste product of animals and modern industry, then we would not likely see that in an atmosphere, but we might see it as a waste product covering the surface of a planet as dirt covers ours, and which is very unlike natural regolith in the absence of life. We might notice a biosignature in the albedo of a planet, that it wasn't reflecting certain expected wavelengths, as those were being used for natural photovoltaics, much as plants use certain frequencies for photosynthesis. If they'd spread out over a metallic rock or into space, they would surely alter the planet's spectrum off the natural surface and its expected characteristics. It is inherent to life that it should alter the world around it and evolve so as to use more of the available energy and resources of its ecosystem, which it should also seek to expand from into new niches, and thus it is inherent to life that it should leave some signature. But if you are a vast whale skinned in quartz and titanium, swimming around the subsurface magma pockets of a planet that makes Venus look hospitable, it would be hard for us to find you. Indeed, strictly speaking, such things might dwell deep below Earth, but that would be a topic for another time too. In the end, for the topic of silicon-based life, while it shows some promise as a plausible option for life, we are left with far more questions unanswered than we would like, and can do little more than speculate for now. But as we venture deeper into the mysteries of the universe, finding new exoplanets every day, we are reminded that our own world is an enormous canvas upon which nature paints many surprises, and on which strange life thrives in the most hostile circumstances. And yet this world is but a pale blue dot compared to the cosmos, which is a near infinite canvas on which even stranger tales might be painted. The possibility of silicon-based life forms challenges us to cast aside our preconceived notions and explore the uncharted territories of existence. Whether we find these exotic organisms or not, the search for them broadens our horizons, as the horizon of this universe is very broad indeed, and doubtless it contains wonders we have yet to even dream of. We spend a lot of time on this show discussing the Fermi paradox and SETI, the search for extraterrestrial intelligence, and one of our concerns is always if we're searching in the right places, which is usually looking for some Earth-like planet with liquid water on the surface. Today we saw how alternative life chemistries like silicon or ammonia, if they exist, might mask alien life from our current SETI hunt. But another of those assumptions is that we are hunting for civilizations, that those are necessary for the development of technology and that they remain so, but there is a possibility that at a certain level of technological development, large civilizations are no longer needed and become viewed as a threat to survival, a world in which anyone can print their own spaceship up or their own doomsday device, so long as they have access to energy and raw materials. Many might flee into the depths of space or even to the galactic rim, for life is a hermit, sneaking into star systems only long enough to claim some more fuel and resources, and we will be examining that in our episode The Fermi Paradox Hermit Shoplifter Hypothesis. That's out now exclusively on Nebula, where you can not only see every regular episode of SFIA a few days early and ad-free, but all our other bonus content, including extended editions of mini-episodes, and more Nebula exclusives like ultra-relativistic spaceships, dark stars at the beginning of time, life as an asteroid miner, nomadic miners on the moon, space freighters, retro-causality, orc OR and free will, conformal cyclic cosmology, colonizing binary stars, and more. Like next month's Nebula exclusive, Giant Space Monsters, that will continue our look at strange alien biologies. Using my link and discount go.nebula.tv/IsaacArthur and my code IsaacArthur, Nebula is available for just over $250 a month, but this holiday season we are once again offering lifetime memberships to Nebula for $300, part of which goes directly to our show, and part to help raise capital for a number of creator-owned projects we are greenlighting for 2024. Instead of a monthly subscription, lifetime memberships are a one-time payment where you can get access to everything that's on Nebula now and in the future, including our growing catalog of exclusive movies, plays, shows, documentaries, and more. And right now for the holidays, you can even gift a lifetime membership of Nebula's life-changing and stimulating content. Monthly, annual, or lifetime, whichever you choose, you not only get access to all the great stuff Nebula offers, you will also be directly supporting this show. Again, to see SFIA early, ad-free, and with all the exclusive bonus content, like Hermit Shoplifter Hypothesis, go to go.nebula.tv/IsaacArthur. We already had a bonus episode this month, Orbital Defense Platforms, but it is a bit of a custom to write an episode about the future as we approach New Year's. And as a futurist, I usually do something more of a deconstruction of predictions, and I decided we would do another this Sunday as a bonus episode for the holidays, where we'll ask if we will truly colonize space. Then we'll finish the month and year with clearing space debris on the 28th, and our final livestream Q&A on Sunday, December 31st. And then we'll move into our 10th year here on SFIA with a return to the Fermi paradox and a look at pancosmorial theory, and the idea that colonizing other planets around distant stars may simply be ecologically unfeasible. Then we'll have a bonus episode on atypical satellites like the Statite, Lagite, and Quasite on Sunday, January 7th. Make sure to hit the like, subscribe, and notification buttons to get notified about those upcoming episodes. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content, like this month's Nebula exclusive episode, The Hermit Shoplifter Hypothesis, at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.